Bismillah ar-Rahman Rahim. So let us consider this problem. Consider an experiment that consists of testing two integrated circuits that come from the same silicon wafer and observing in each case whether a circuit is accepted A or rejected R. So we're testing two integrated circuits, right? Each can be either accepted or rejected. The sample space of the experiment is this: reject, reject, comma, reject, accept, reject, and accept, accept. So that B denote the event that the first chip is rejected. Similarly, let A denote the event that the second circuit is a failure. Find the probability of A, second chip is rejected, and B, first chip is rejected. Given the following probability model: probability of reject is 0.01, probability of RA is 0.01, probability of AR is 0.01, and probability of accept is 0.97. So also find the conditional probability that the second chip is rejected, given that the first chip is a reject, right? So to summarize again, the sample space of this is given, which is here: reject, reject, R, A, AR, and AA, right? And the probability of each outcome is also given, right? So probability of R 0.0, it's very small probability that both get rejected, and then probability of RA, it's again very small probability that one gets accepted and the other gets rejected. Similarly, the probability of AR, accept, reject, is also 0.01, but the probability that both get accepted is very high, which is 0.97. And you know that the probability model, if you sum all this probability together, so this is 1, which is the probability of the total sample space, which should be actually be 1. So now the event A is the second chip rejected. It can be expressed mathematically. The second chip, R here at the second place and R here at the second place, it comprises of these two outcomes, right? And the event B is first chip rejected. So R at the first place here again, and then RA. Mathematically speaking, this is the event B. So we are going to find the probabilities of event A and event B, right? So probability of A is actually the sum of the probabilities of these two outcomes. Probability of this outcome plus probability of this outcome AR. So we already given these probabilities. So the probability of event A is RR, probability of R is 0.01, plus probability of AR is also 0.01. So the probability of event A is 0.02, right? Event A was second chip rejected. This is the probability of second chip rejected, and note that this is prior probability, right? Similarly, the event B, the probability of event B is the probability of these outcomes, probability of RR plus probability of RA. So probability of B is probability of RR is 0.01, and probability of R is also 0.01. So probability of event B is 0.02. So this is again a priori probability. So priori probability for both these events is the same. So probability that the first chip gets rejected is 0.02, and probability that the second chip gets rejected, the prior probability is 0.02. In both cases, the outcome, the probability of this event is the same. So let's now find out the probability of that is second chip is rejected, which is actually event A, right? Given that the first chip is rejected, which is event B. So we are now interested to find probability of A given B, and this is equal to probability of A intersection B divided by probability of B. So from here we can find the intersection of A and B. A intersection B is simply this event RR, right? And the probability of A intersection B is equal to the probability of this event RR, and this is 0.01, right? And we already know, we have calculated it, the probability of B. So we can put in the values here now. So probability of A given B is A probability of A intersection B is 0.01 divided by the probability of event B, which is 0.02. So probability of A given B is 1 over 2 is equal to 0.5, right? So the probability of A now has changed, given B is now changed from this A priori probability of A, right? So this is only 0.02 and this is now 0.5. So the partial information that we received, partial related information, right? The event B is related to in the event A. Both these integrated circuits come from the same silicon wafer. So if the first integrated circuit has been found to be faulty, then the second, the likelihood of the second being faulty rises, right? So the information has affected the probability of that event. It is now much greater than the prior probability of that event.